Everyone. Welcome to problem 2.28 of David Griffiths Electrodynamics. All right, let's jump in. So the problem statement says to use equation 2.29, which is this equation here for the potential, to find the potential inside a uniformly charged solid sphere of radius r and a total charge of q. So I'll just write q here. So essentially what we have is a solid sphere, it's not hollow, and so it's uniformly charged with a charge density of we'll call it rho, and we want to find the potential at some point p inside of the sphere, and I've decided to orient p so that it's on the z-axis, which, you know, really you could think about it, no matter where you choose p, you could rotate the sphere or your axis to always have that point on this whatever axis you choose, right? So I'm just orienting it so the point is on the z-axis for convenience. And then I've kind of defined an origin here. We have a radius r. We have, you know, this is some arbitrary point where charge exists in the sphere. You know, this point could be, you know, less than z, or it could be greater than z, all the way up to the radius at least. And then I have the separation distance between this point and this point, script r. So, and this is the equation for the potential. So we will start here. And so real quick, we can easily define, you know, our charge density function, which is a function of r prime in general, is a constant. So it's just going to be rho. And then our separation distance, since this is not a right triangle, this could in general be any kind of triangle, but we know at least two of the sides is z and r for the distance. And so using the law of cosines, we can say that r is the square root of r squared plus z squared minus 2rz cosine of theta. If you're unfamiliar with the law of cosines, I would suggest looking that up. This is a very handy formula to know when you have a general triangle like this that's not a right triangle. What else? So the differential, we're going to be working in spherical coordinates here because that's the most obvious and convenient coordinate system. So our differential volume charge in spherical coordinates is r squared sine of theta dr d theta d phi. So that's you can find this in the front of Griffith's book or the back or whatever, I forget where, if you forget what the differential volume charge is in spherical coordinates. And so that basically gives us everything we need to plug into our potential equation and start solving an integral. So let's take all this and plug it in. So the potential, so we're going to have, I'm going to pull out the rho since it's a constant, so we'll have rho over 4 pi epsilon naught, keep all our constants out. And this is going to be a volume integral. It's going to be a triple integral here. So we're going to have one integral of phi from 0 to 2 pi. Phi here is the polar angle around on the xy plane. So that's going to go all the way around. And then I guess we'll have d phi. We will have a theta integral, which actually I'm going to do that first. The r integral I'm going to put second. So r is going to go from, you know, just 0 out to the radius. And we'll have our r squared dr here. And I know we have in this term an r and we have r's and thetas. So, you know, we have to evaluate this with respect to r or theta first, and it's easier to do this with respect to theta first. And then once we get rid of the thetas, then we can worry about the r integral. So then we have theta is going to go from 0 to pi. So from this thing, you know, theta starts along this axis and goes all the way around to pi, which would be down to here. And we will have just the square root of, now we'll have sine theta on top, d theta from our differential, and then r squared plus z squared minus 2rz cosine of theta. So I think that is good for our integral. And quickly, let's just get rid of this phi integral. So the integral of d phi from 0 to 2 pi is just 2 pi. So that's easy. And I'm going to go ahead and I'll write that in the next step. But to solve this theta integral, we can let u, we're going to do a u substitution. No trig substitution needed. So we're going to let u equal this term in the square root. So this is going to be r squared plus z squared minus 2rz cosine of theta. I'm doing that because I see cosine of theta and sine of theta, so it should be easy to eliminate that. And so real quick, du then would be du with respect to theta, so that's 0, 0, and then the derivative of cosine of theta is minus sine of theta, so that becomes a positive 2rz sine of theta d theta. And so sine of theta d theta is equal to 1 over 2rz du. So sine of theta d theta will replace with 1 over 2rz du, and then all of this can just be replaced by u. And so we're going to have this 2 pi, we'll have 2 pi rho over 4 pi epsilon naught from the phi integral. And then we're going to have the r integral 0 to r, we have the r squared, oops, dr, oh man, I messed this up. Just pretend we'll just do that. And then our bounds are going to change, so this is going to be u now, and when theta is 0, cosine of 0 is 1, so we get r squared plus z squared minus 2rz, and then when theta is pi, it's minus 1, so it becomes a plus, and so we get r squared plus z squared plus 2rz for our bounds. So we have some weird bounds going on, but it's going to work out. Sine of theta d theta, well, that's just this, so we have the 1 over 2rz, and then we have the square root of u du. And so I'm gonna trying to think of how I want to deal with this. So yeah, these are just constants. So this integral is pretty easy because you can think about this as u to the minus 1/2, and then you can do your simple integral that way, power rule. So you add 1, so it becomes u to the positive 1/2, so that's just the square root of u. Divide by positive 1/2, so you multiply by 2, and so what we end up with is, I'm going to cancel out some terms, so we get a 2 here, and then we'll have a 2 multiplying, so that's going to cancel this 2, so we'll just have 1 over rz there, so it ends up being rho over 2 epsilon naught out here. We have r going from 0 to r squared, 1 over rz times the square root of u, and we need to evaluate this from r squared plus z squared minus 2rz to r squared plus z squared plus 2rz. So I guess technically I could cancel an r here. Let me just think. Let me take a look at my notes. Yeah, okay. Cool. So let's write this out. So we have rho over 2 epsilon naught. Then we have an integral from r being 0 to capital R. Then we have r over z, which is just, we can ignore that for now. And then this is going to be the square root of r squared plus z squared plus 2rz minus the square root of r squared plus z squared minus 2rz, and then dr, I believe. I guess I forgot to write a dr up here technically. Yeah, that looks about right. Okay, so now there's a relationship here that will simplify these two terms. So we can end up writing, I'm going to go to the next page. So the square root of r squared plus z squared plus 2rz is equivalent to r plus z, and the square root of r squared plus z squared minus 2rz is equivalent to, well, the magnitude of r minus z. You can kind of write it like this. We can use this to simplify our expression here. So then our integral becomes, well, we have that rho over 2 epsilon naught, and we have the integral from r0 to capital R, and have r over z, and then we have r plus z minus the magnitude of r minus z dr, and this magnitude is because of I believe this minus sign and the square root, and to do this integral, what we can essentially, because r and z are not fixed. I mean z is like technically a fixed point, right? But r can be sometimes less than z, and r can be sometimes greater than z, and so we can have different cases going on. And so if, let me write this here, if r is greater than z, right, so we have this expression, r plus z minus the magnitude of r minus z, right? That's our expression. If r is greater than z, then this is going to be a positive number, so we can just drop the, it doesn't matter, right? The magnitude sign doesn't matter. So we end up with r plus z minus r plus z, so the r's cancel, and we get 2z, we get 2z there. And then if r is less than z, then we can flip it around, right? If this will be negative, and you can just flip those two around to make it the same magnitude, I guess. And so that becomes r plus z minus z plus r. So the z's cancel, and you just get 2r. So we have these two different sort of cases to consider here. And we can split this integral up, going from, instead of 0 to r, we can go from 0 to z and then z to r, and that's what I'm going to do. So we have rho over 2 epsilon naught here, and we're going to have, I'm going to do this. So we have an integral going from r equals 0 to z, and in this range we use, I believe, let me see. So we have this r over z still. So actually, okay, let me write this out one more time, like one more step. Let me like distribute this through. So, well, okay, so if I distribute this through on this case, right? So if I multiply this by r over z times r over z, what we end up getting is 2r here. I think this is 2r squared over z. Or, sorry. Yeah, that's right, I think. Sorry, I'm just double checking with my notes here. Make sure I do this correctly. And we end up with, so we have the integral going from little r 0 to z. And I have 2r squared over z dr. So this is where r is less than z. So we're going from 0 to z. So we're in this case. So we have this integral, right? Then we have the other integral where r is going from z to big R. So, or in this case, so r is greater than z. And we just have let me see, 2r dr. Yep, that is right. Okay, so that is our integral. So I hope that makes sense. Because of this magnitude sign, we kind of have two cases to consider, and so we can kind of split our range up. Like our integral becomes different between like in these two cases. So we have to split this integral up into these two integrals so we can get the both cases correct, or both of their contributions. And so this is going to end up being, these are easy integrals now. So we have, this will be 2r cubed over 3z from 0 to z plus 2r squared over 2 from z to r. All right, so those are the integrals, and now we just have to plug in their bounds. So let's go ahead and do that. So we have rho over 2 epsilon naught out here. So this first bound is easy. So we have, it'll just be 2/3 z cubed over z, which just becomes z squared. And then we have here, so we're going to have the 2's cancel. So we have r squared, it'd just be r squared minus z squared. Oh, but this 2 here, hang on. It'll be this, because this 2 here doesn't cancel. Sorry, I had that wrong. This 2 is out here. Sorry, this does not cancel. This is still a 2. This is still a 2. It'll be like this. And I guess, yeah, technically it can cancel. However, what I want to do is pull the common 2 out and cancel with this 2. So technically it could cancel. I just want to do it a different way. Since we have 2's here, I want to pull it out and cancel that 2. So this is going to be equivalent to rho over epsilon naught. And then we have z squared over 3 plus r squared minus z squared over 2. And we can get a common denominator here. I'm just going to simplify this further. So you can get a common denominator 6, right? So we have rho over epsilon naught, and we end up with 2z squared over 6, and then plus 3r squared minus 3z squared all over 6. And so 2z squared minus 3z squared, we can combine that. I'm just trying to simplify this as much as possible. So that's going to be, so we have 3r squared over 6, and then 2z squared over 6 minus 3z squared over 6 is minus 1z squared over 6, right? And then I can cancel the 3 and get a half here. It becomes r squared over 2. So rho over epsilon naught, we get r squared over 2 minus z squared over 6. And just trying to see, let me look at my paper real quick. So if I pull out a 2, or yeah, if I pull out a 2, yeah, let's just pull out a 2. So then finally, we're going to have v of r is equal to rho over 2 epsilon naught. And if I pull out a 2, then we get r squared minus z squared over 3. Oops, z squared over 3. And I think that's about as simple as I can go. And very quickly, you can express this in a different form if you plug in, so rho here is the charge density, which is going to be the total charge Q on the sphere, divided by 4/3 pi r cubed. So if you plug that into here, you can get this in terms of the total charge Q on the sphere, which will be, so we have Q, we have 3Q over 8 pi epsilon naught r cubed times r squared minus z squared over 3. And if I distribute an r squared through and a 3 through, what we end up with is Q over 8 pi epsilon naught r. So I'm distributing r squared through and a 3 through, and we get 3 minus z squared over r squared. And so this and this are equivalent to each other. All right, that covers it. That is because it says to, yeah, I guess it didn't technically say to express it in terms of the total charge Q, but that's just another way to express it. So yeah, we end up with a nice little answer here for a solid sphere. So I hope you guys were able to follow along with this, and if you guys have any questions, feel free to ask, and I will definitely answer them. So thank you guys for watching. I really do appreciate it. If you want to support this channel, check out my Patreon link below. You can subscribe, and I will be soon doing these videos on a tablet and uploading the PDF solutions to my Patreon account so that you guys can access them that way as well. So thank you all for watching, and have a great day.